MSG3, Volume 1 for fixed-wing aircraft, and Volume 2 for rotorcraft provide the industry-wide standards for developing scheduled maintenance programs. For years, the systems section of these documents utilized a specific, rigid procedure for identifying maintenance-significant items. However, the structure section lacked a similarly standardized selection process. The legacy MSG3 structure section focused on definitions, explaining the characteristics of a structurally significant item, or SSI, without outlining a repeatable procedure for identifying them on a new airframe. This procedural gap led to inconsistencies across different aircraft programs, as individual engineering teams were left to interpret these high-level definitions during the analysis phase. These inconsistencies specifically impacted how engineers assess the risks of secondary damage from detached parts and the structural requirements for carrying human external cargo. Without a specific set of procedural steps, even a precise definition is subject to interpretation, which often results in different analysts reaching different conclusions about the same component. To address these variances, the IMRBPB issued CIP MPIG 2026-05, a paper designed to standardize the identification of load-bearing structures. This update centers on a specific change. The term categorized has been replaced by selected. The previous term, categorization, allowed for a sorting process where items could be grouped without meeting a strict technical threshold. By contrast, selection requires the manufacturer to apply specific safety filters to every item, ensuring it only reaches the SSI list if it triggers at least one critical safety gate. This creates a new default state. If an item does not meet the specific criteria of the selection questions, it is automatically routed into the zonal or other structure category. This update aligns the identification logic for structures with the binary, filter-based logic used for systems maintenance. Transitioning the language from categorization to selection changes the engineering workflow from an administrative sorting task into a data-driven filter. This filter-based philosophy is codified through a new 4-step procedure. Step 1 requires engineers to apply 3 safety questions to all structural zones. The first gate asks if the item carries flight, ground, pressure, or control loads, and if failure compromises safety. The second integrates Issue Paper 192, focusing on consequences of a component failure. Engineers must determine if an in-flight failure or detachment could, through secondary damage to other systems, prevent continued safe flight and landing. The third gate applies exclusively to Volume 2 for rotorcraft, addressing the specific risks of external load operations. Because structural failures in a hoist system can lead to fatal injuries for external personnel, these items are now analyzed through a dedicated safety gate. By embedding these scenarios into the initial checklist, the procedure ensures risks like secondary damage and external cargo safety are evaluated alongside primary loads. Step 2 uses simple Boolean logic. If the answer to any of the gate questions is yes, the item must be analyzed as an SSI. In Step 3, these items are compiled into the official candidate SSI list and presented by the manufacturer for review. Step 4 requires the working group to review this list and apply MSG3 analysis to validate each selected item. This review ensures that no critical items were missed and that the analysis is performed at the highest manageable level of assembly. Because structural requirements can change during the analysis phase, the SSI list is maintained as a living document and referenced in the Policy and Procedures Handbook. This standardized workflow forces a cross-functional review, ensuring the SSI list is finalized through collective validation rather than individual assessment. This text-based procedure is supported by a visual logic map, designated Figure 2-4-4-2. For Volume 1 fixed-wing aircraft, the diagram illustrates a clear path for every structural component. Every structural item defined by the manufacturer enters, though, at the same starting point. The first decision node assesses if the structure contributes significantly to carrying flight, ground, pressure, or control loads. If the answer is yes, the item is immediately routed for SSI analysis. A negative result sends the component to the second node, which evaluates the potential for secondary damage during in-flight detachment. A component is only routed to the other structure bin if it yields a negative answer at both the primary load gate and the secondary damage gate. Mapping the procedure this way creates an auditable record of why each piece of aircraft architecture was or was not selected for intensive structural analysis. Volume 2 specifically adapts this visual logic architecture to accommodate the unique aerodynamic and mission-specific operational needs of modern rotorcraft. The rotorcraft diagram begins with the same load assessment and secondary damage nodes. For most components, the path is identical to the fixed-wing model. However, Volume 2 logic includes a third decision node for human external cargo. Items lacking primary load or secondary damage risks aren't dismissed until clearing this gate. Components necessary for HEC safety route directly to the SSI list. Only items yielding 3 negative answers become other structure. Integrating HEC requirements into the visual flowchart ensures that these mission-critical components are systematically captured in the safety analysis. CIP MPIG 2026-05 provides a standardized method for identifying load-bearing structures across all aircraft programs. Replacing the passive sorting of items with an active selection filter ensures structural analysis is applied where it's most necessary for safety. Secondary damage from detachment is now a permanent, required consideration in structural maintenance planning. Similarly, human external cargo structural safety is now a primary logic requirement for all rotorcraft. These visual logic maps unify the analysis of fixed-wing and rotary-wing aircraft while respecting their unique aerodynamic risks. SSI identification has moved beyond a set of definitions. It is now a standardized, auditable procedure that ensures consistent structural integrity across the global aviation industry.